scroll up. So this is 2019, right? Chemistry Unit 1, Paper 2, right? So we're gonna look at Module 1. Question 1 here. This is the hydrogen spectrum, right? So explain how the emission spectrum of hydrogen is produced. How is it produced?
Sir, by
Wait, hold on. Let me see. Use your hands. If you guys use your hands, you're gonna see like who came up first. So like it's a little bit better, other than like trying to speak at the same time. So you guys just use like the raise hand feature, please. So what is it? So what would be the first thing in your explanation? Okay, so I was wondering like since nobody. Okay, so go ahead, Nikela.
okay, sir, it's produced by electron.
Explain how. So walk me through the steps.
Okay, so electrons gain energy and are able to move to higher energy levels. They will eventually lose energy and fall down to lower energy levels. So it's based on electron transfer, like not transfer, but like transitioning, from different energy states.
So let's say within a gas chamber, I'm just using this as an example. Sorry, chamber, right? Hydrogen gas, H2 gas, right, is right. Well, we're gonna have H2 gas, right? Is bombarded with high energy photons, right? Makes sense. So we bombard them with high energy photons, right? The energy, right, from these photons will be absorbed, right, by the electrons on hydrogen. So we get that by absorbed by electrons on hydrogen, right? These electrons will become, wait, hold on, let me see this. Photo excitation, right? So these electrons, let me fix these, some of the words may be wrong. Electrons will become energized and move, right, or transition to a higher energy level, right? This leads to them being highly unstable, so they will, right? So they will fall to their original energy level, right? This fall requires the exact amount of energy that was absorbed to be emitted. The energy emitted will be in the form of light energy and be detected by, I guess, well, be read by the detector, basically. That's a lot. Somebody raise their hand. Identify the series of lines here. What would be the series of lines? What would be the series of lines here? What would be it?
Balmer.
Balmer.
The Balmer series. Alright, so going with that, this would be the Balmer series. Oh, not the Blammer, but the Balmer. The Balmer series. Alright. Here, assess how the series of lines provides evidence for discrete energy levels. Somebody tell me that. Somebody explain. Go ahead.
So the different wavelengths that are produced, and they correspond to different. It's proportional to the energy, and so depending on how many states above its ground level the hydrogen, well, the electron goes up, then different wavelengths will be produced because it takes more energy. So yeah, I'm not really sure if I'm explaining it right. It's just that the different wavelengths correspond to the different energy levels. And then you add some more stuff.
Okay. Somebody else add? Alright. So what I'm basically saying here is that the energy, right? Remember that the energy required to for electron transition, right, is quantized, right? So it is specific to energy levels, right? So that means that the emission here, right, shows an energy level specific, well, shows energy specific to an energy level. So it's this one and this one and this one and this one, right? They are specific and discrete because the energy, right, required to absorb is really specific. It's a specific energy, right? And that will emit the same amount of energy, right, that is absorbed after the electron will become unstable, right, and release that energy and go back to its original state. So what we're saying is that the lines, right, show discrete energy levels because the energy required for electronic transition is specific, right? It is quantized. So there can be no transition between energy levels, right? That's why it really shows this type of emission spectrum. Right? So when light is absorbed, the electrons transition, right, to different energy levels, right? And then they release light, well, release energy, right? When this energy is mapped, right, it shows that there are only specific areas that, you know, the electron can be transitioned to, and that proves quantization, right, and that there are discrete energy levels, right? If you require a specific amount of energy, that means that there's a specific energy level that you're going to be occupying, right? So it's something similar to that. Alright, so the answers are there. So well, let's look at this. Draw the electron transitions occurring between energy levels associated with the origin of the lines in the visible region of the hydrogen spectrum. What will be the answer? Someone tell me.
So they're falling to n equal to.
You sure?
Yes, sir.
Sure.
Yes, sir.
Alright. Remember that here is Lyman series. Here is Demo. So what? Balmer. Here is Passion. And it goes all the way up. Alright, so I have different series here. Hydrogen combines with oxygen to form the compound water and is also present in the hydronium ion. Alright? Write the electronic configuration for oxygen in SP notation. What is it?
S2S2O2P4.
Alright. Draw the shapes of the S and P orbitals. What's the S orbital?
So it's a sphere. It's just a circle.
Or just draw the complex diagram and then draw the mathematical function. Lol. It's just a. Oh wow! And we say that chemistry is difficult. P orbitals, no.
So it's a dumbbell, you know. It's like an infinity sign along different axes.
It really doesn't matter which axis you put on it, right? It's just that you draw it, right? With the axis labels, right? Alright, so we have those. What's happening here? Use VSEPR theory to deduce the arrangement of the orbitals and shape or bond angles of each of the following hydronium ion. Yeah. So water at the oxygen atom in the molecule of water. Repeat.
Sir, is it nonlinear?
Bent. Or alright. So it's saying that
104.5.
104.5. 0.5. Alright, that's the one angle. For hydronium, what would hydroxonium, what would it be?
Tetrahedral.
So it's gonna be and what's going to be the bond angle? 107?
109.5.
Oh, 109.5. Right? So now we will have to talk about that now, you know. Right? So you will have to speak about electrons. Right? So you know, electrons in the bonding pair, how does that relate to lone pair electrons? How does that relate to literally everything, right? So bonding pair versus bond pair, lone pair versus lone pair versus bonding pair, right? Speak about those type of things, right? For the valence shell electron pair repulsion theory. So you're gonna have to speak about that. Explain why the density of ice is lower than expected. Right? We saw this already. This repeated. So we're saying that as water molecules cool, right? Their movement is slowed, right? And we have intermolecular reactions being formed, right? So when these intermolecular hydrogen bonds are being formed, the water molecules actually spread out from each other, right? To arrange themselves in a lattice structure which is more stable, right? So they arrange themselves in a lattice structure, and because they arrange themselves in a lattice structure, they are less dense, right? So they take up less, well, they take up more of a volume, right? So yeah, so do we understand like why the density of ice is lower than water though? We spoke about that.
Yes, sir.
Alright, we spoke about that before. Here now we're gonna have the bond energies here. So nitrogen, so we're gonna have a nitrogen bond there, plus we're gonna have 2 hydrogen bonds here. Boy. Alright, and we're gonna have this is reactants. Right, for products, we're gonna have, what are we gonna have for products? We're gonna have NH3, so we're gonna have 3 NH3, well, NH bonds, NH bonds, right? Plus, no, it's gonna be 6 NH bonds. 6 NH bonds, alright. So it's gonna be 6 NH bonds. Alright, so we're seeing that. Let me check everything over now. That would be 1, 2, 3, 1. Alright. So the energy of the reactants would be what? We have nitrogen being 945 plus 3 hydrogen, so 3 times 4, 3, 6. What would be the answer for this? Hello? What would be the answer?
Sir, 2,253
kilojoules per mole. Alright. For products, we have NH would be 309 times 6. Sorry, 309 times 6. So what would that be?
2,340. 309, sir, or 390?
300. 390. Oh, sorry for that. 390. Sorry about that. So it would be the same thing?
Yes, sir. Yes, sir.
Repeat.
Yes, sir.
Repeat. Like what the answer was.
2,304.
And this is bond formation or bond breaking. Somebody raise their hand, go ahead.
Sir, the one for hydrogen is wrong.
The one for hydrogen is wrong?
Yes, it's 1,000.
Wait, hold on, what's happening? We're
So,
adding
I raised my hand in regards to the question. Wouldn't it be pyramidal instead of?
Wouldn't it be pyramidal?
Yeah.
Oh, alright. So note that.
And the angle would be 107.
Beautiful. Alright, so you were able to see it. Because I was going to go over it, you know. Because remember when I asked if it's going to be 107, and I hear 119, I'll just put 119. Because we're working with what we're saying and then we'll go through it. So 107 would be pyramidal. Alright, so what's happening here? So what is the answer for this? The nitrogen bonding, well, bonds plus the 3 hydrogen bonds. What's the answer for that? 1,003 what?
308.
Right, and that's, you know, kilojoules per mole.
1,845.
Wait, hold on. Somebody said something. I'm not hearing what you're saying.
That's just for hydrogen to hydrogen.
This is for hydrogen. Okay, I wanted the full answer, you know, guys. I want the full answer for everything.
So yes, sir, the full answer 2,253.
2,253, the same thing was there.
Yes, sir.
Alright, well, hold on. Okay, kilojoules per mole. Right? And then we have this kilojoules per mole. So is this bond formation or bond breaking for products?
So bond forming for products, sir.
So it'll be negative.
Yes, sir.
Let me fix that then. Then we're gonna have products minus reactants, right? Product minus reactants?
Well, I mean, sir, that would give you like -5, 12, 4,000 or something. So I don't think that's me. I think you just combine them, like what we did for the last question.
So what is the equation though?
Well, the equation is products minus reactants.
So wouldn't it just be products minus reactants? Like it's an equation. By essence of it being an equation, no matter what you have, you should get the answer if you plug in the values, right? So it shouldn't just be products minus reactants. So what you said the value would be and why you think it's wrong?
So we're using the product as -2,340, right?
Mm-hmm.
Yeah, but if you minus the 2,253, you'd get -4,593.
Or so you're saying that feels wrong?
Yeah, it feels wrong.
What type of reaction is happening here? This is the Haber process. What type of reaction? Endothermic or exothermic? You should be able to tell.
Yeah, I think it's exo.
So we have 4 bonds up here. 6 bonds forming. Let's see what we have, what we're gonna have through the reaction. So the equation says this, and you feel that it's not going to be right. This is what the equation says: products minus reactants. And what was the answer you said you would get for this?
Negative 4,593.
And that's kilojoules per mole.
Kilojoules per mole.
So your plan is to not use the equation to get the answer?
Well, there is not. Well, I'll probably just not use the minus for the products, and just know that it should be exothermic and put the negative sign. Like what we did for the combustion in the 2022 paper.
Yeah, but wouldn't we have ended up doing the same thing there?
No. So for that question, we didn't put as negative. We just kind of subtracted them normally.
Okay. So for these, when you're doing the equations for them, right? When you're doing the equations for them, what does... You guys did enthalpy already, right? With your wonderful chemistry teacher. So what did they tell you for this? What should we do in this case? Should both of them have positive values?
Well, I could just put them. So if you're using bond energies, you just have to add them.
Just to add them.
So just have to make both form negative is the product and just combine it.
Okay. Let me check the chat in case their person is typing and I have absolutely no idea what they're saying. Let's have a look. So you're saying we should just add them together?
Yes, sir.
Do we agree? Does everyone else agree? Is anybody agreeing in the chat? Because I don't hear anybody on meeting, so I guess.
That's what we did for the last one.
Alright. So we would just add them. So if you add them, what would you get?
Negative 87.
Negative 87 is the answer. We should get negative 87. Not hearing what you're saying. Repeat.
So I'm saying that you could just put the sign after since you already know what reaction is supposed to be.
Yeah. I get what you're saying. Because I remember negative 87 being the answer for this question. Albeit years ago, but hold on. Yeah, it's this question, negative 87. So we're just gonna add them then. Because what we could just do is put the negative behind, and then if you have two negatives, you just get a positive, right? So outline experiment to determine the heat of solution of ammonium nitrate. In your response, include those. We did this. We looked at this, on the other paper. It's the same thing that we discussed before about the calorimetry, basically. You remember the entire thing? So do you remember the thermometer, and then that the thermometer will be held by a clamp. Like, I think you guys know how to like draw it. So that would be your thermometer. Right, and then over here would just be the solution. Right, and then this would be just be your clamp, your retort stand. Right, so you would know how to do that. Oh, and then you know you have your styrofoam. Cup. Alright, and you guys, how the data to collect is determine the heat of solution. How do you determine the heat of solution? What is the heat of solution? How do you calculate the heat of solution? Asking you guys. Nobody knows how to calculate the heat of solution? Or do we? Alright, so seems that I've lost connection.